So now that we understand semi-direct products as an alternative way or an additional way to build new groups of old out of old ones, just like products gave us such a way to do this. The question is does this account for every single way of building new groups? Well, we've already seen that the answer is no, right? There's, for example, only so many ways to build a semi-direct product of Z4 by Z2. And for example, this does not include the group of quaternions, which also has a normal subgroup of order 4 and a quotient group of order 2. So something else has to be going on here. And what we're going to explore in this video is other extensions. Now, today's video is going to be rather long and technical as we slowly and carefully go through the details of one particular tool on how to classify extensions in the case where A, the normal subgroup, is abelian. In the next video, I am going to try and make that more computational, which may also be boring in different ways. But this video, the goal is to very carefully find a way which will allow us to describe all extensions between two groups, A and G, when the normal subgroup is abelian. So that's what we're after today. Okay, and I've got a bunch of notes with me because it is complicated. So how did we proceed previously? Well, before, when we had a semi-direct product, the key was that we had a section. So that was a map S from G to E, where pi composed with S was the identity. And essentially having this section is what allowed us to then construct E as a semi-direct product of A and G. But the important thing was that S was a group theoretic section. So that is to say, S was a group homomorphism such that this condition was satisfied. What we're going to do now, so what happens in the more general case, if E is possibly not a semi-direct product, we're now going to allow ourselves the greater generality where S need not be a group homomorphism. It's simply going to be a set theoretic section. Now, if we started with some set theoretic section, S, we could define another one, which would be SG times S at 1 inverse. Then this is still a section because pi t g, of course, is pi SG S1 inverse. Pi is a homomorphism, so this is pi of SG. Pi of S1 inverse, but because pi is a homomorphism, that we can pop that inverse out here. And so this becomes G times, 1 inverse times the identity, so it's just G. So this is still a section, and it's sort of related to S. So, but the point is that this section now, T has a property where if we evaluate T at 1, then we see that this will just be the identity of E, right? So we call this a normalized section. So this is a normalized. So we can assume that the section we started with, S, is a normalized section. Okay. Now, if S were a group theoretic section, right? So we want to account for the case when S is a group theoretic section, or rather, we recognize that there's a possibility that it may fail to be. We know it's surjective, so there has to be a set theoretic section. But if we're accepting the fact that it can fail, sometimes when something fails in mathematics, we want to measure that failure. So we could consider the following function, SG, SH. So this is a function that, takes in pairs of elements. So it's SG, SH, and then SGH inverse, right? And notice that this function, right, from I guess, this is a function from like G cross G into E. This function would just be the identity function in the case that S is a section. And also notice that, again, pi of this function, again, I can separate this out into pi of each of the individual factors, and just like before, I can pop that inverse out. And the point is that this, because S is a section of G, this becomes G times H times GH inverse, which of course is the identity. So what does that mean? Well, that means that this expression here is in the kernel of pi. But the kernel of pi, because we started with an exact sequence, we know that the kernel of pi is exactly equal to the image of A. Oh, apologies. I don't think so this is the same name that we gave before. I don't think I gave a name to the inclusion here, I, right? So, well, what does that mean? That means if this is in the image of I, that means there has to exist some element of A, where if I apply I to that element, I will get SG, SH, SGH inverse. Okay? So, and now this element depends on whatever choice, on whatever G and H are here. And so what I'm going to do is I'm going to get a function, now a function that goes from G cross G into A. And it's a function of two variables. And so the output of the function, so we just argued that we know that there has to be an element that goes here, where if we apply I, we get out this term. And in fact, because this sequence is exact, we know that I is injective. And so this is actually well defined. There is one element that will do the job. So there's at least one, and there is only one. So that is how I define this function f. Okay. And now let us consider the following fact about our newfound function. So I of fg1 is by definition SG S1 S1 time G times 1, which is just G inverse. And since this is normalized, this is just equal to 1. And so these two terms cancel out. So this is the identity. And this is the same as writing S1 SH inverse, which would be the image of I under F1H by definition. So the point is that because I is injective, we know that this means that both FG1 and F1H, these are equal. These must be the identity. And actually, I'm going to write this as 0 because A is an abelian group. So I prefer to write that notation additively. Okay. So, a lot of technical stuff. What's the point? Maybe I should throw you a bit of a bone here. So the point is, from this function f that we've recovered, here's what's going to happen. From this function f that we've recovered, this is going to now allow us to fully describe the group law on E, and essentially we're going to get a bijection where we send E to these functions, And in certain cases, for each one of these functions, we can construct such an extension E. Now, there's some caveats to this that we're going to get into technical details of, but because we just waded through a whole bunch of technical details, I figured I should maybe explain where this is all going. So it's giving us a tool by which we can classify all of the possible extensions in terms of these special kinds of functions. Okay. So how do we do that? How are we going to build this group law for E? Well, remember back to what we did in the semi-direct product video. So what was happening there? Remember that we had something, so like, again, A includes into E, surjects onto G. And remember, we wanted to see what a group law was like. We were trying to mimic the product, right? And we wanted to multiply a pair of elements where we had something on the left from A and I guess something coming from G and something coming and another element. So what should I say? If it was like a product A times G, right? So maybe I'll go back and look at the semi-direct product video where we wrote something like this. We had these two terms, right, that we wanted to think of like AG times BH. And we wanted to try and recreate the group multiplication in the product scenario. And we ended up inventing the semi-direct product along the way. And the thing that we did to try and turn it into a group homomorphism was we tried this conjugation trick, right? So that trick worked for us last time in the case of the semi-direct product. Why wouldn't we try and apply that trick again, right? So because I want, the goal would be to rewrite this as I times something times S times something, right? That would get us back this sort of product formulation. So why don't we try that trick again, since it worked so well for us before? So here we're going to do the same thing. So we have, let me just make sure I get this right. So we have IA, SG, IB, SG inverse, SG. So it's just that favorite mathematician's favorite trick of multiplying and dividing by 1, right? So we insert this term in here, right? And the point was, because A is a normal subgroup, we know that this will be in A. So we know that this will be I of something, right? And so we might think, oh, well, we're there. But the thing that worked in the last time was that S was a section, and so we knew that we were able to rewrite this term as SGH, which that completed the proof, right? But we don't have that now, right? S is only a set theoretic section. So we're not necessarily allowed to make this move. And we can see actually already from this point in the proof, we can see that we exactly recover the case of a semi-direct product precisely when S is a set theoretic section. So that's really nice. But what are we going to do? What are we going to do in this case? Okay. So let me write something a little bit different. We're going to have to go on a slight tangent here to describe things. Gosh, let me get my notes ready. Okay, so suppose that we had some element y in G, and that we had some element x in E, where x maps to y. And by the way, maybe I will write this as I of D. We do know there is some element D that makes this true. So let's suppose that this were the case. Well, since I is a normal subgroup of E, or rather, sorry, the image of A under I, we know that for any U in A, Y, I, U, Y, this is going to be back in A, right? Because it's a normal subgroup. So that means we can choose a V in A such that I of V is equal to Y I U, Y inverse. And now, bear with me for a second. So maybe I should pause again here to give you the idea of what's happening. What did we do before? We ended up basically saying, what did we get out of the semi-direct product thing before? G acted on, we ended up getting G, a homomorphism from G into the automorphism group of A. Of course, we used different notation before, right? But that was sort of the punchline takeaway. We got a homomorphism from G into the automorphisms of A. In other words, we got an action of G on A. And so essentially what I'm claiming is we're getting a new action here. So I can define the action of G on B to be this D that we get out of it, right? So essentially I'm saying that we still get this out of the story as before. And so in order to do that, though, this kind of depended on the I suppose the pre-image we took, and I guess I want to convince you that this gives us a well-defined G action. I mean, I suppose it already does give us a well-defined action because S is we can always fix it with respect to S, but I want to show that this actually doesn't depend on the choice of pre-image. So to show it's well defined, right? If I get this, action, I don't want this V to depend on my pre-image X. So I suppose that I have some other Z in E, which also maps to Y. Then what does that mean? X and Y determine the same coset, right? These determine the same coset. Of the image of Y, of the image of A. And this means that, oh, boyja, I've yoboinked my notation. This means I can choose a Y, a W. I can choose a W in A, such that what? Such that Z is equal to XIW times X on the left here. So what does that mean? That means that ZIU Z inverse is XIW. Wait, this should be IU. This should be XIW IU XIW inverse, which is XIW IU W inverse. I'm gonna pull that inside because that's a group homomorphism, and this is additive notation in the abelian group. X inverse, which now this is XIW plus U minus W X inverse, which of course is XI. The W's cancel out. I'm left with U X inverse. So what was the point of all of that? The point was is that we get, hence, we have a well-defined G module action of G on A. Right? That was the whole point. What do I mean by a G module? Technically, I mean, what I mean is that I have a I have an action of G on A that respects the abelian group structure. So in particular, G dot U plus V is equal to G dot U plus G dot V. This is my claim. Actually, I'll prove this for you. So all I mean is just that we have a group action which respects the addition. Why would we say the word module? You might know that a module is something that happens over a ring. Well, this is, in fact, this does sort of naturally give rise, if I form the ring of all functions from my group, from G to Z, then I can define, this extends to an action, right? I have a basis of this ring is going to be given by the indicator function, which just evaluates to 1 if x is equal to g and 0 otherwise. And now for this ring, I can define the action of 1g on some element of A to be this G action above, and then this extends to a well-defined action. Okay. Why would that matter? Well, this actually is going to be a very important concept further down the line when we start talking about cohomology. It gives us one possible perspective on this whole thing. But okay, perhaps I should show you that this gives us, that this respects the Z module action. Oh, and so what's the other thing I wanted to say here? Actually, there's something more important before I move on to that. The crucial step in all of this is right here. Why is this crucial? Because I have used the fact that A is abelian, and that is what allowed me to swap, basically to commute these two terms and to have the two W's cancel out and just end up with I of U down here. That is critical in all of this. So you may have wondered at the beginning of the video, why am I only, because certainly there's other kinds of extensions, so why would I only focus on extensions when the normal subgroup is A? We can do it more generally, and I will make videos talking about the more general case, but life gets more complicated, and so it's very crucial that we're using that assumption at this stage. Okay, so how do we know that this respects the G module? How do we know that this relation holds? So let's go back to the proof, and let's think about this fact. So, well, suppose that we had, suppose that G dot A were equal to B, and G dot C were equal to D, described in the manner that I described these relations up above. So what does this mean? Well, this means that we can choose an H in E such that pi H is equal to G. And what else? Well, where? So H I A conjugated by H has to be equal to I of B, right? That was like the definition of the action. And H of IC, H inverse, is ID, right? So if I multiply these two things together, I get H, well, let me just say, multiply these two equations together, right? What do we get? This H is going to cancel with this H, and I'm going to be left with H, I, A plus C. I can pull those in because it's a homomorphism, H inverse, and then multiplying the other two sides together, this becomes I, B plus D, right? And so therefore, by definition, this says that G dot A plus C is equal to B plus D, but B was G dot A and D was G dot C. So, okay, that takes care of that proof. And moreover, I want to know that this is a well-defined, I'm claiming that this is a G action, right? So it should also be the case that this is compatible. What do I mean by that? I mean that for any G1, G2 in G, I mean, what we want to show is that G1 times G2 acting on A is the same as G1 acting on G2 acting on A. I think I wrote it the other way in my notes, but let's choose again HI for I equals 1 and 2 such that pi HI is equal to G. Then what are we going to do? Well, it's the same trick as before. So G1, well, what should I say? Rather, observe that H1, H2, IA, H1, H2 inverse. Well, this is H1 of H2, IA, H2 inverse, H1 inverse. And so, in fact, we do see, yes, G1, G2 acting on A. I mean, I already wrote the relation up here. Okay. So, where does that leave us with everything? We have a lot to get through. I might break this into more episodes. So, well, we've constructed a well-defined group action. Now, I'm claiming to you that we should be able to recover this group, the group E, up to isomorphism in a similar way, starting with this this product thing here. So why don't I lasso this? Because I do live in cowboy country. And let me drop this down here for you. And now that we have this well-defined G action, we can write this in a bit of a more compact notation. This is going to be IA times I of G dot B for our action. But now we're left with this term SG SH here, right? And the problem was that in the other case, that was a homomorphism. So what do we do in this case? Well, we can rewrite it. So this is IA, I, G dot B. And remember, we defined F to be the function where I of FGH was going to be SG SH S of GH inverse. So if we move this second term over, we can replace this term with I of FGH, and now we have an SGH here. So by introducing this F, that's what allows us to, even though this is not a set theoretic section, allows us to recombine these terms. And now this is exactly because I is a homomorphism. Now we've recovered something that looks exactly like what we wanted, and essentially what we had in the case of a semi-direct product. So we have I times something, I of something times S of something, right? And in fact, we can see that if F were the zero function, we would actually recover the semi-direct product. This is exactly what we got for the semi-direct product. So it's just interesting. It's just nice to see every step of the way where exactly this is a generalization and where we're using this. So I claim for you that this entirely determines the group law. So I claim that now I'm going to define a new group called E sub f. And just like with the semi-direct product, I'm actually going to define it on the Cartesian product. So the underlying set is going to be the Cartesian product. But how do I define the group operation on here? Well, it's exactly defined by this. So I define the group operation, right? AG times BH. I'm going to define it to be A plus G dot B plus F of GH and GH. Okay. Great. So exactly mimicking that. And what is my claimed isomorphism going to be with the group E? Well, I'm going to send a G. I'm going to send this to I A S G. And so we can essentially see by this argument that we've actually carried out above, starting from this term and ending up on this term, we can actually already see that this is a homomorphism. So that part is done, essentially by construction. But of course, we'd like to know that this is an isomorphism. So let's take a look. Well, so suppose that this landed in the identity, right? So suppose we had some element that whose image was the identity. And I need to look at my notes. And what is this? This is IA SG inverse. And so, well, this would imply that or sorry, no, just SG. And so this implies that I of A inverse, which is IA inverse, is equal to S of G, right? But then I know that the image, right? I know that this thing, the image of A under this inclusion is the kernel of pi. And so I know that I would get out the identity of G if I applied pi to this. But that's the same as applying pi to S, and S is a section of pi. And so this must be G, and so I conclude that the G component is the identity. But then, what does that mean? Well, I have 1 being equal to phi of A1, which is IA S of 1. Remember, I chose S to be a normalized section. So this is IA, but the map I is injective, and this implies that A is equal to 0. So in fact, yes, my term AG has to be the identity. In other words, the only thing that maps to 0 under phi is 0, 1. And so therefore the kernel is trivial, and therefore phi is injective. Okay. How do we show surjectivity? Good question. Okay, so let's suppose that we have some arbitrary, I don't know, G, So let G be some arbitrary element of E. Well, then pi G is going to be in G. That's what I'm going to choose for my factor on that side. And moreover, pi of S of pi G, of course, is going to return pi G. And so therefore, we know that S of pi G and G have the same coset. In this quotient. Therefore what? Therefore, we know that G is equal to S of pi G times IA for some A. Hence, well, and then we're done. and then we're done. Why are we done? Well, actually, because they're in the same coset, I can actually choose to write this. I'm instead going to choose to write this on the left. And now we see that actually G, this is phi A pi G. And so G does get mapped to under this. Okay, so the map is injective, the map is surjective, and we're done. Well, I think that's where we're going to leave it. Actually, there's one last thing I want to tell you before I end this video, and that is not only did we recover the group, so not only were we able to redescribe this group E in terms of this function that defines it, so much like in the same way of semi-direct products, we sort of had this action, but now there's also this extra datum of this function. In fact, we can recover the entire exact sequence. So what I mean by that is we have, this short exact sequence here. And yes, we have an isomorphism, phi, abstractly of these groups, but I claim that something even stronger is true. I still have an exact sequence where here, this is the map that sends A to A, 1. And over here, I have the map that is going to send A, G to G. So this gives me a short exact sequence. And in fact, if I put equal signs here, I get commuting diagrams, which is to say I actually get an isomorphism of short exact sequences. So it's somehow an even stronger statement. So that is where we're going to leave things off for today. So I know it was very long, sort of technical. The next episode, because we're not done, is also going to be technical. But let me review for you one more time what the punchline is. We started with the general problem of trying to understand extensions of groups. We said that, okay, if we add the extra assumption that the normal subgroup is abelian, then knowing nothing else about this, I am able to put a G-module structure on A, and I am able to describe a function that goes from the Cartesian product, not a group homomorphism, but a function that goes from the Cartesian product of G to A. And from these two things, I am entirely able to recover the group EF. So, in other words, if I want to understand extensions of a group by an abelian group. It actually suffices for me to completely understand G-module actions on the abelian group and functions. But, and this is going to be the focus of the next video, it's not just any kind of function. As you can imagine, this function is going to have to satisfy certain special properties in order to guarantee that we actually get a group. So we've seen one part of this bijection so far, where we've started with an extension of these groups, and we produced from it a function. The question for next time will be, well, what are the special conditions we need on this function so that I could just start with an arbitrary function and an arbitrary group action, and from those two things construct a group? Well, see if you can beat me to it, but for now, QED.